hopefully winning the award for longest title in any presentation today, or this conference. I'm Oliver Hunt. I work at Apple. I work primarily in the compiler team, but my job is at the intersection of compiler engineering, PLT, and platform security. And that's what I'm going to be talking about today. We're going to be looking into mitigating use after free security vulnerabilities in C and C++. And there's a whole pile of words here, and not everyone in the room is going to be familiar, so we're going to actually introduce a bunch of these concepts. Things like what a use after free error is, why they're bad, and then we'll talk about type isolating allocators and how they are good. And then we'll talk about what we actually did inside Clang at Apple to try and bring these two things together to make the world a better place. But fundamentally, use after free error is a particular class of memory safety vulnerability that is very highly exploitable. It is also very difficult to prevent statically inside C and C++ code just due to the nature of how these languages work. And what makes it particularly highly exploitable is that at OpenC, fundamentally it is I have used a piece of memory after I have freed it and after it has been reallocated as something else. And this creates a very, very exploitable primitive because it introduces a path to type confusions down the line and future memory and corruptions of the heap and corruptions of user data, of your program's data. The fundamental problem here is that an attacker can use this error to get control over data that you would otherwise consider trusted or consider useful to contain a specific kind of information. And this can be used to give remote code execution, elevate privileges of a piece of code, or just generally corrupt everything in your program state. And one of the mitigations we've introduced progressively over the last decade is the concept of a type isolating allocator. A type isolating allocator's basic idea is the core exploitable element of a use after free bug is the subsequent type confusion. So if we ensure that we can guarantee that a single piece of memory or a single address in your address space is only ever used for a specific type or a specific subset of types, you can drastically reduce the power of the primitive or the power of the error. This means that you get the ability to prevent attackers from conflating pointers and user data, pointers and control data, and things like that. And this kind of defense, or this mitigation, is effective in a number of different security-sensitive environments. At Apple, we've deployed it extensively throughout XNU, the kernel for iOS and macOS, through the kalloc type system. And this kind of mitigation is also used extensively in all modern browsers, through a variety of different libraries, things like libpass, partition alloc. And to a lesser extent, there are third-party independent libraries, things like isoalloc, that provide a similar functionality for other environments. The underlying problem, however, or the problem that we've been trying to address, is that the manual adoption of type-based isolation is very expensive. It requires a lot of annotations, requires a lot of work and a lot of adjustments to existing code. And the reason for this is because you do need to provide that type information to your allocator. If you've said, I want my allocator to separate different types of memory, the allocator needs to know what a different type of memory is. And this is difficult in existing code because the overwhelming majority of allocation APIs are untyped. If you think of your malloc or POSIX memo line, these things just take I want this number of bytes. They don't say, I want the bytes for this type. And then we get to another issue, which is fundamentally C-based languages don't have the concept of a type that is usable as a runtime value. And as a result of all of this, the overwhelming majority of existing C and C++ code is written in terms of entirely untyped APIs. So to try and mitigate this, we introduce the concept of typed memory operations. And what these are is an annotation that a library author can use to notate that this is an allocation API this allocation API has a typed equivalent that you can use instead if you're aware of this, if you have support for this feature. And then Clang will do the heavy lifting of migrating the code over to that. And it doesn't do this this is not a port your code or a manual rewriting or update or anything that involves changing your code, the code that is in your repository. This just happens automatically as part of the code generation process. The annotation lets you specify what your type entry point is, and it also provides you an ability to say, hey, this particular parameter is the thing that is going to contain the type information. And then you can perform your inference over that. Compiler will perform inference over that. And we will then subsequently call your typed API. Currently, we've just got this up as an RFC on LLVM.org. And we're going through some feedback process on that. The fundamental model, just to give an idea of just how lightweight this is from an annotation point of view, is what we have here. As a library author, you just add your declaration for your type entry point, and then you attribute your allocation API with this is what my type entry point is, and this is the parameter I want you to infer over. So malloc is a particularly trivial case because it's a single parameter, but there are plenty of other APIs that people have, and the annotation extends to those. Once you've done this, what happens during code gen is Clang looks at your call sites, looks at the expressions that you pass that you've said, this is what I want as a type, and then simply replace that call with the call to your typed entry point, and it will pass in a type. And we're just going to leave what that type is for now, and just say this is the general model of how this feature works. But of course, we do need to actually represent that type. As the example indicated, we kind of care about this for general system allocator level APIs, which means there is a much higher code size constraint than there is in many other cases or individualized cases. So we've had to focus on minimizing the impact of binary size. And we also have to deal with another problem, which is we're inferring a type, which means the types that we infer may not actually exist as a C or C++ level type in the source. People often just do single allocations where they combine multiple types together. And then even once we do have that type, we do need to provide some semantic information about the type. It's not just a matter of saying, I have a type name. We need to know what that type contains. And to that end, at Apple, we've developed a type descriptor. And the type descriptor is just a very compact representation of a type that tries to achieve every single goal we have whilst making no trade-offs whatsoever. Unfortunately, that was not possible, so we made a bunch. It is a single 64-bit value where we have reserved a set of bits in that value to provide semantically important information about the type, and we'll get to that, as well as an identity of the type. There is no additional metadata beyond the 64-bit value. It is not a pointer. Which means the total overhead of this is the cost of passing a 64-bit parameter at the call site. Currently, the information we provide is very, very basic core elements of a type. Things like, is it a polymorphic type? Does it have a v-table? Are there unions? We know from prior experience with security vulnerabilities that attackers will frequently target objects that do intermingle do overlay different types together. So unions seem like something that are semantically relevant. And we have other things like, does an object contain a pointer? An object that contains no pointers is less overtly attackable than something that contains pointers. And an object that contains a code pointer seems even more valuable as a target. In addition to that, we also want call site information, because again, from prior experience, we know that there is a difference in the attackability of a memory allocation of a fixed size versus a non-fixed size, and a difference in the semantic behavior of an array allocation versus just a general blob allocation. By providing the semantic information, we allow a allocator to provide a more nuanced approach to how it isolates types. as it is not necessarily feasible to just say every single unique type gets its own unique storage. That has a significant memory cost. But just having the semantic information is not sufficient. It's not enough to say, I want to keep data types separate from objects that from types that contain pointers. We still need to know we still need to have some unique identifier for a given type, because you want to, in addition to keeping data away from pointers, you want to keep pointers in different objects away from pointers in other objects. And for that reason, we have a type identifier. And a type identifier is a structural hash of the type. We're not concerned about the name. We're not concerned about the C-level idea of what a type is. What we do is we linearize the type. Essentially, you can think of this as being a product of the struct layout algorithm. And then we can enumerate every single byte in that type and say, this is the kind of data held at that byte. And the goal here is not to produce anything that would be useful for a reflection point of view. The goal here is to create an idea of a type where different types get a different number at the end, and the same types get the same number at the end. Having done this, we can then hash it all together to get into the space we have available. This is what is derived from the work we did a few years back to support X and U's k-alloc type model. It's just made more compact because of its more generally widespread usage. And the typeness of that is, there is a very compact idea of what a type is. If we do care about something being a pointer, we don't care about what it is a pointer to, unless beyond these things like code versus data versus something that might be pointer authenticated, as Anton might be familiar with. And we still have to get to the automatic adoption that I have been promising you. This is done by a very, very basic concept of type inference. We know that there are a number of standard allocation patterns that people use, standard expression patterns. And from that, we can try and work out what types are being allocated at a specific location and try and build out from there. There's no particular priority in this list. This is just to give you an example of the kinds of patterns we're matching against. It's going to be obvious extended as time goes by. And I included the type of T plus type of U example just to give you an indication of the idea of the situation where we might have a type that does not match anything at the C level. But we also have to deal with the fact that this inference can fail. It's a very basic inferencing. The ability for people to do things with C is large and unending. And when push comes to shove, it is possible for people to just pass a random integer to malloc. So whilst this works as a default option, and in our experience it covers most cases, it can still fail. And there are common idioms that will defeat the inference. We have things like wrappers. It is not uncommon for people to have helper wrappers around malloc, things that will do a check to see whether I return a null pointer and crash or whatever. And similarly, even more subtle things like a style guideline. If you have something like the LLVM style guidelines, which say you must not have more than X characters in an expression, people break their code up. And this inference, for performance reasons, is very, very localized. Doesn't require any flow control or anything like that, which means that breaks the inference. There are ways you can work around this. In the wrapper case, we have provided a built-in called built-in TMO get type descriptor, where you can just pass the type or the expression, so it works with macros nicely, and it will produce you a descriptor that matches the kind of descriptor the inference would produce. At Apple, we have deployed this across multiple platforms, across the entirety of user space on our platforms, in fact. And we have not noticed any significant code size or runtime impact. We've not noticed any impact on build times. And the overwhelming majority of call sites successfully infer what type is being allocated and infer that correctly. Now, I know a lot of people here are more interested in C++ than they are in C. And C++ does provide a slightly different environment from C. C++ memory allocation is actually semantically visible. Unfortunately, whilst it is visible to the compiler, whilst it is visible to the user, it is not visible to the allocator. And to that end, Louis Dion and I have proposed P2719 to the C++ committee, which is a language level specification for type-aware allocation and deallocation functions. What this does is it increases the explanatory power of operator new and operator delete to actually say in a way that is visible to code what type is being allocated or deleted. It is a fairly self-explanatory model. The only reason for the type identity T flag is because we need some way of distinguishing between existing code and these type allocators. So type identity is an empty struct, so it has 0 cost. And I do mean literally 0 cost. It's a 0 size struct in all modern APIs. A 0 size struct does not take a register or anything like that. If you are on an environment where you're wanting to use type memory operations, you're obviously going to care about how the C++ model interacts with the TMO model. And it's a fairly simple one, which is you can just use the built-in that we provided to give you the type descriptor, and this just overlays through, and it's semantically and practically identical. Anyway, in summary, we've introduced an attribute that lets you annotate untyped API to provide an automatically adoptable typed version of that API. That annotation allows Clang to automatically redirect calls to the untyped API to the typed version. It provides enough information for an allocator to make meaningful security and policy decisions that have adjustable and actually effective performance metrics. And we have proposed an RFC for this, and based on some feedback, we've started discussing ways to add additional schemas rather than just a specific type descriptor model. And we briefly touched on the C++ proposal, which provides a more standards path-based approach to this particular problem. And with that, and 2 minutes to spare, questions?
Where's questions?
Sounds like it was flawless. Is that a question? Oh.
So you didn't mention too much about what happens inside the allocator with this. Like, does it affect the memory overhead? Like, what happens there?
That's an allocator implementation detail. What we've done is made it so that we provide enough information for the allocator to make its own decisions. I alluded to it briefly. There is a platonic ideal of the allocator ensuring that a piece of memory is never used for any kind of separate, distinct type at all, and every single type gets its own memory for all time. The cost of that is too high in the general case. And what we've tried to do is make it possible is provide enough information for an allocator implementation to coalesce allocations in a way that provides decent performance whilst also allowing reasonable security trade-offs. Huzzah. Thank you very much.
Thank you. So quick.